All right. Today we're going to be talking about double angle identities. Double angle identities are useful when you know the sine and the cosine of an angle, and you need to find the sine or cosine of twice that angle. So our first double angle identity is sine of 2 alpha equals 2 times the sine of alpha times the cosine of alpha. For the cosine of 2 alpha, we can either use cosine squared alpha minus sine squared alpha, or we can use 2 times cosine squared alpha minus 1, or we can use 1 minus 2 times sine squared of alpha. Next, we're told that the sine of theta is 3/5 and that theta is in quadrant 2. So we're supposed to find the sine of 2 theta and the cosine of 2 theta. What we should do for this one is start by setting up a triangle, which I think you can see. I hope so. For this triangle, it's in quadrant 2. The opposite over the hypotenuse is 3/5. And so if we use the Pythagorean theorem, we'll find out that this side length is 4. This 4 will be negative because the x is negative here. So to find the sine of 2 theta, we need to use 2 times the sine of theta times cosine of theta. We know that the sine of theta here is 3/5. The cosine of theta will be adjacent over hypotenuse, negative 4/5. Positive times a positive times a negative is negative. Let's change this to a fraction. 2 times 3 times 4 is 24. 1 times 5 is 25. So our answer is negative 24/25. Next, the sine of 2 theta. For this one, we could use any of the three identities. Doesn't matter. They will all get the same answer. So for this one, I'm just going to have us use the first. Cosine squared of theta. We said that the cosine of theta is negative 4/5. So we need to square that minus the sine squared. Sine is 3/5. And so negative squared will become positive. 4 times 4 is 16. 5 times 5 is 25. Since we have common denominators, we can subtract 16 minus 9 is 7, and so we have 7/25. Our next example asks us to simplify using double angle identities. 2 times the cosine squared of 12 degrees minus 1. Now, when I look at this expression, it doesn't look anything like sine of 2 theta or cosine of 2 theta. But if we look at what cosine of 2 theta equals, we see a 2 times cosine squared of alpha minus 1, which is very much like our format here. Our alpha is 12 degrees. So what we can do is we can rewrite this expression as the cosine of 2 alpha, because that's what this equals. So we've got cosine of 2 times alpha. Now what is our alpha? Our alpha must be 12 degrees. So we substitute 12 degrees in place of this alpha. 12 degrees here. And so this equals the cosine of 24 degrees. Next, we have 8 times the sine of 3x times the cosine of 3x. Look at my 3 cosine identities, and this doesn't look like any of them. But it does look close-ish to my sine double angle identity. Except instead of a 2, I've got an 8. Now I can fix that. I can change this into a 4 times 2, and that'll be the same thing. So now we have 2 times the sine of something times the cosine of that same thing. And so, for the purposes of this example, 3x is our alpha. So we can write 4 times the sine of 2 times that alpha. Sine of 2 times that alpha. We said that our alpha is 3x. So this will be 2 times 3x. And so 2 times 3x is 6x. Next, we need to prove that the secant of 2 alpha equals secant squared alpha over 2 minus secant squared alpha. So to begin, I'm going to work with the left side. I'm going to change this to 1 over cosine of 2 alpha, because we know that cosine of 2 alpha is one of these 3 things. There's all of those 3 things. So in place of cosine 2 alpha, I'm going to substitute the second one, because that just has cosines in it. I look over here and I see that I've just got secants. Secants and cosines have their relationship. So I don't want to introduce any sines into the situation. So we have 1 over 2 cosine squared alpha minus 1. Next, cosine is the same as 1 over secant. So this becomes 1 over 2 times 1 over secant squared alpha minus 1. Now, 2 times 1 over secant becomes 2 over secant squared. So this would become 2 over secant squared. Now I want to combine these 2 terms down to my denominator. To do that, we need common denominators. And so I'm going to multiply this one by secant squared over secant squared. Secant squared over secant squared. Now that we've got common denominators down here, we can subtract the 2 fractions. So we've still got the 1 up top, 2 minus secant squared alpha on the bottom, over secant squared alpha. Now I've got 1 divided by a fraction, so we can keep, change, flip. Secant squared over 2 minus secant squared. 1 times this fraction will equal this fraction, which is exactly what we wanted to prove. Next, we need to evaluate the cosine squared of 75 degrees minus sine squared of 75 degrees. I look at this and I see that that is a lot like my first version of the cosine of double alpha. So what I can do is I can rewrite this as the cosine of 2 times our alpha. Our alpha here is 75 degrees, and so that would be 2 times 75 degrees. In other words, that is the cosine of 150 degrees. And we can figure out the cosine of 150 degrees. 150 degrees is going to be in quadrant 2. It's between 90 and 180. So 150 degrees here. That means that this is 30 degrees. So we can set up a 30, 60, 90 triangle. Meaning that we'll have a 1 unit side across from the 30, a negative root 3 across from the 60, and a 2. We need to find the cosine, and so that will equal the adjacent over hypotenuse, negative root 3 over 2.